Welcome to Schrodinger's Clubhouse. I am your host Dragonborn, and this is part 2 of my coverage of electromagnetism, and my second video in my series covering the 4 fundamental forces of the universe, or reality, whichever one you prefer. My first video I talked about electrostatic forces, and in this one I'm going to talk about the other side of electromagnetism, the magnetism part. So let's get into it. One thing I'm going to bring up from my previous episode, if you haven't seen it before, is essentially electrostatics is the static side of electromagnetism, meaning the whole principle of charges and all that doesn't actually need something to move. On the other hand, the magnetic side of electromagnetism is more dynamic. For something to be magnetic, all the electrons have to be aligned, which doesn't exactly happen without something dynamic happening. Also, an electric current or moving charges can actually induce a magnetic field. And one of the things that actually, if you're wondering, this is the same as the bar magnet that I'm using now, and this is actually the equivalent of the magnetic field of the Earth. This is an exact, or the magnetic field of something spherical. It's not exact, but it gets the point across. So, when it comes to magnetism, it's different from electrostatics. Like, with electrostatics, something can have a charge and not have the other charge near it. Electron will have a negative charge for all eternity until it either decays into something else or it literally becomes another particle. Magnetism, on the other hand, is always bipolar. There's always a north and a south part. Again, something I brought up in my first one, the names don't matter. We could have one be the elephants. We could call one the elephant pole and the rhino pole. We just use north and south because it's more convenient. So, one thing that oftentimes is brought up when you're talking about magnetism and electromagnetism is magnetic flux. And magnetic flux is how much a magnetic field is changing. So, a magnetic field really doesn't do much other than either attract or repulse. Oh, and now I bring that up, when it comes to attraction and repulsion, the same thing applies to magnetism as it does to electrostatics. Opposite poles attract, and like poles repel. So yeah. Now, the common misconception is that, and this is oftentimes displayed in media and all that, oftentimes it's said that any form of metal is magnetic in some way. However, that is false. Only certain types of metals, only ferromagnetic materials respond to magnetic forces. So, something like this, which would be made up of iron, if I'm correct, either iron or steel. It would be technically iron and steel are essentially the same thing, but steel has more carbon in it. So things like iron are ferromagnetic. Also, so is nickel and cobalt. Metals other than that, like for instance, if you try to bring a magnet to a copper penny, that's not going to do anything because the penny is not ferromagnetic. Now, just because it isn't ferromagnetic does not mean it doesn't respond to magnetic forces. In fact, everything has magnetic forces, again, tied to the whole electromagnetism thing. It's the thing that holds atoms together. And this was an experiment done. What this group of scientists did was they took a non-ferromagnetic material, they put it in the center of a big machine, and what this machine was made to do, it produced the strongest artificial magnetic field that humanity has produced. And what happened was it actually caused the thing to start heating up. So even things that aren't ferromagnetic, like another thing, neutron stars. So basically, this is essentially what happens when a star, all I'm going to say is when a very massive star, not massive enough to become a black hole, but more massive than a star that would create a white dwarf, that would turn into a white dwarf when it dies. A star, when it goes supernova, if it doesn't have enough mass to become a black hole, it becomes a neutron star. And neutron stars are essentially giant, like the equivalent of giant atoms, but instead of being held by electromagnetic forces and a strong nuclear force, they're held together by massive gravitational forces. Again, later I'll touch on gravity on another video. The reason I pulled up neutron stars was because they actually spin very rapidly, and when I mean very rapidly, I mean multiple times a second. And the fastest one that these are called pulsars, because their fast rotation causes them to emit radio waves. And there's the fastest one that we've observed, spins 175 times per second. So, yeah. And one byproduct of this, because again, the whole magnetic flux, and the whole thing about magnetism being the more dynamic side, this very fast rotation causes a neutron star to have a magnetic field so strong that it literally bends atoms when they enter this magnetic field. It is a trillion times stronger than Earth's magnetic field. So everything responds to magnetic forces. It's just how much magnetic force you need in order to actually bend non-ferromagnetic materials, as opposed to something that responds at a lot less magnetic force. And one of the last things I'm going to cover, out of all of the fundamental forces, the final thing I'm going to touch on this episode is actually the strength of these fundamental forces. So the strongest of them all is the strong nuclear force. It holds atoms, it holds the atomic nuclei together against, remember, if you see the first one in this series, you'll understand why the strong nuclear force has to be stronger than electromagnetism in order to keep atoms together. So, the strong nuclear force is the strongest of them all, and while you might hear several different opinions on this, the second strongest, it's oftentimes, a lot of people will say it's one or the other. This is more variable, but one of the things I've seen repeated the most is that electromagnetism is the second strongest. The third strongest is the weak nuclear force, which is essentially the whole reason for atoms needing to decay in the first place, and basically allows for nuclear reactions to happen. I'll touch on the weak nuclear force and the details about it on another video in this series. And the weakest one is actually gravity. It's actually kind of surprising, but the weakest one is actually gravity. As evidence, this magnet is holding this thing, this steel piece, and it's clearly You know, you oftentimes hear about something like people saying it's impossible to defy gravity, but when you really get down to it, I'm defying gravity. I'm making this thing defy gravity right now. That's the strength of electromagnetism, and because of the force carrier particle for electromagnetism, it technically could extend infinitely, but in nature, you can never get the right the right formations in order to get electromagnetism to extend as far as gravity extends, as the gravitational force extends. Like, for instance, how the sun's magnetic field extend, it's called the heliosphere, the heliosheath. It protects the Earth from dangerous cosmic rays that not even our magnetic field could protect us from. It does extend to a very far distance, but the sun's gravitational pull is even stronger, because past that, it's called the Oort cloud. So, yeah, I'll be wrapping up this episode. If you like this kind of science content, please like this video and subscribe to my channel. I have more videos like this that are already there, ready for you to watch. If you have any comments or questions, put them down below in the comments below. If you have a science question after I finish this series, I'll actually answer those science questions that you put down in the comments below. I hope you have a great day, and let the science be with you.